Okay, so far we've looked at a bunch of different types of integrals. We looked at what happens when we have a product of functions, and we tried integration by parts. And then we looked at different type of trig integrals and also trig substitution. So in 8.5, what we're going to do is we're going to look at rational functions because we really haven't talked about that yet. But first, what I would like to point out is that if you have an integral where the integrand is 1 over x plus some number a, and here the coefficient on x is 1, okay, then you don't really have to do a substitution. That's just going to equal to the natural log of the absolute value of x plus our number a. So you're free to use that without using a u substitution. So our strategy when we try to evaluate rational functions is to break it down into smaller pieces. So we're going to look at some cases. The first case we're going to look at is if we have linear factors. Okay? So linear factors are factors where the exponent on the x is 1. Okay? So if we have some sort of rational function where p and q are polynomials, then what we're going to try to do is we're going to try to break down the rational function into some smaller pieces. So the first thing we want to do is, in this first example, is we're just going to decompose the integrand. We're going to make it into little pieces, but we're not necessarily going to evaluate this integral. So what we first want to do is we want to factor our denominator. So this quadratic will factor as x plus 1, x minus 2. So our integrand, 2x plus 1 over x plus 1, x minus 2, we're going to break that up into two fractions. So break it up into smaller pieces and maybe will be easier to integrate. Okay, because notice this integrand, we can't integrate that. Even if we did a u substitution, it wouldn't work. So maybe if we break it down into little pieces, it will be nicer. So what we have to do is we have to figure out what the numerator is going to be. So we're just going to let the numerator of our first linear factor be a, and then we're going to let b be the numerator for our second linear factor. So the strategy here is to solve for a and b. We have a problem. The problem is that we have one equation and three variables. We have x, a, and b. So maybe if we can get rid of x and then have two equations with both a and b, we can solve it using algebra techniques. So the algebra techniques you're going to use are actually the algebra techniques from high school algebra. I'm going to show you two methods. But before we go into the two different methods, the first thing we want to do is we want to clear the fraction by multiplying both sides by the LCD x plus 1, x minus 2. So our equation is going to be 2x plus 1 equal to a times x minus 2 plus b times x plus 1. And now your books, or your ebook, is going to have you do one technique. I'm going to show you another technique. It's very simple. And this technique works really well when you have linear factors. So what I'm going to do is I'm going to strategically pick x. Say x is equal to 2. So if you look in this term x minus 2, if x is equal to 2, that would be 0. So I end up with this equation. Let's see, 2 times 2, I get 5 is equal to, and then b would be, it would be 3b. So right away I find that b is equal to 5/3. So now I'm going to get rid of the term with the b in it by strategically picking x to be -1. And if x is equal to -1, the equation becomes -1 is equal to -3a. A is equal to 1/3. And I'm done. I'm done. Okay, so I can break up this integrand into 1/3 over x plus 1 plus 5/3 over x minus 2. And I'll do that in just a little bit. What I'd like to do is go over the second method, and this is what your book does. By the way, this method always works. It's just longer. Okay? So I'll call this method 2. In method 2, we're going to start out where we did before, after clearing the fractions, to get 2x plus 1 equal to a times x minus 2 plus b times x plus 1. Okay, so we're going to go ahead and get rid of all the parentheses, and we're going to combine like terms on the right hand side. So 2x plus 1 is equal to ax minus 2a plus bx plus b. 2x plus 1 is equal to, combining the x's, I have a plus b times x. I don't like the negative in the front, so I'm going to do plus b minus 2a. Now, in order for this equation to be true, it must be true that the x's match up and the constants match up. And the only way that's going to happen is if 2 is equal to a plus b and b minus 2a is equal to 1. So this is the method that your My Math Lab will do. And at this point, you have two equations with two variables. You can solve it by elimination or substitution or your favorite algebra principle. What I see right away is in this second equation, if I add 2a to both sides, and there's many ways you could solve this, I get 2a plus 1. So now that I have the b isolated, I can substitute that into the first equation to get one equation with the variable a. 2 is equal to a plus 2a plus 1. And we have 2 is equal to 3a plus 1. Solving for a, we get 1/3. Which is what we got in the first method. Now that we have a is equal to 1/3, we can substitute that into our equation to find b, which is equal to 2 times 1/3 plus 1. And then b is going to be equal to 2/3 plus 1/3, or 1, sorry, that would be 5/3. But what does all this mean? Well, what this means is, and now here we're going to go back to our original integrand. That means that we can break up our integral. So this integral here is going to break up to the integral of 2x plus 1 over x squared minus x minus 2 dx equal to a was 1/3, so 1/3 over x plus 1 plus b was 5/3 over x minus 2, okay, and this is all in the same integral. Breaking that up into two separate integrals, I could pull out the 1/3. This is the integral of 1 over x plus 1 dx. Oops. Plus 5/3 times the integral of 1 over x minus 2 dx. And although the problem didn't ask for us to solve it, we're going to go ahead and solve. 1/3 natural log of the absolute value of x plus 1 plus 5/3 natural log absolute value of x minus 2 plus our constant c. Can't forget about that. And we're done. So previously, all those other methods we had, we couldn't solve this type of integral. But now we can by breaking it up into little pieces. And you're free to use whichever method you choose. Let's try another example. Okay. So the key here is to remember your factoring from algebra. Notice that in my denominator in example 2, I have the common factor x that I can factor out. So the first step is to factor out the x to get x squared plus 3x minus 18. And then hopefully that factors further, and it does. It's x plus 6 and minus 3, x minus 3. So our integrand, x plus 1 over, and I'm going to write the factored form, x plus 6, and x minus 3 is equal to, these are linear factors, so I'm going to have a over the first factor plus b over the second factor, x plus 6, plus c over the x minus 3. Now multiplying by the LCD x plus 6, x minus 3 gives the equation x plus 1 equal to a times x plus 6 times x minus 3, wonder if I'll have space, plus b times x minus 3 plus c times x plus 6. So remember that second method. The second method is get rid of all the parentheses, combine the like terms, and then compare both sides. I'm lazy, so I'm going to use method 1. Notice that I could choose x is equal to negative 6, x is equal to 3, or x is equal to 0. I like zeros. If x is equal to 0, then the term with b and c are gone. And I end up with 1 equal to negative 18a. So negative 1 over 18 is equal to a. If I choose x to be negative 6, then the term with the a and the term with the c are gone. Okay. And I have negative 5 is equal to, what is b going to be? Negative 5 times negative 8, no. 54? Negative 8. Oh, negative 6. Negative 9, negative, yeah, that's right. Okay. Negative 5 over 54. That would be equal to, oops, sorry, b. So the last thing I'm going to choose is x to be 3. If x is 3, we have 4 equal, and then we have 9 times 3. So I guess that would be 27c. So c is 4 over 27. So I would like to review method number 2. And method number 2 is fine. It works really well when you have factors that repeat. Notice that all of our factors have been different so far. But it's really long. So think about what we would have to do to actually get rid of the parentheses. I have x plus 1 is equal to, so a, I'm going to multiply these first two polynomials together and get x squared plus 3x minus 18 plus b x squared minus 3x plus c x squared plus 6x, and then get rid of the parentheses. I'll have an ax squared plus 3ax minus 18a plus bx squared minus 3bx plus cx squared plus 6cx. Next step is to line up all the like terms. I notice that the highest exponent is a 2. Notice on the left-hand side I'm missing an x squared, but I can add one in. 0x squared plus x plus 1 is equal to, let's see, x squared. I have a plus a plus b plus c. So I'm going to have an a plus b plus c x squared. And then my x's, I have a 3a minus 3b plus 6c. So it's 3a minus 3b plus 6c. And now the constants. I just have the one minus 18a as the constant. So this is actually a minus 18a. So when we compare like terms, notice that I have a 0x squared, an a plus b plus cx squared. Okay? So it must be true that 0 is equal to a plus b plus c. And then I have this 1x. Oh look, I forgot my x. How typical. And I have a 3a minus 3b plus 6cx. So it must be true that 1 is equal to 3a minus 3b plus 6c. And what's really nice about this last one is we have the constant 1 has to be equal to the negative 18a. And I get my a right away, which is exactly what we had using method 1. Now that we have a, we can plug that into the other two equations, and then we'll end up with two equations with two variables b and c. If I put in negative 1 over 18 for a, this first equation becomes, actually it'd be a positive 1 over 18, because a is negative 1 over 18. I'm going to add it to both sides and get b plus c is equal to 1 over 18. And then if I put negative 1 over 18 in for a in the second equation, that becomes a negative 1/6. So if I add that to both sides, I have a 7. My pen died. Okay, my pen is back working again. If I put in negative 1 over 18, I'll have 7 over 6. Okay, why are you not working? 7 over 6 equal to negative 3b plus 6c. You have to, at this point, recall your algebra and how you would solve these equations. Again, we can do a substitution, or notice that if I just multiplied the first equation by 3, it becomes 1 over 6 is equal to 3b plus 3c. And the second equation was 7 over 6 equal to negative 3b plus 6c. When we add those two equations together, the b's will cancel, and we have 8 over 6. Okay, is equal to 9c. So if we divide both sides by 9, I have 8 over 54 is equal to c. And then 8 over 54 divided by 2, that would be 4 over 27. And that's exactly what we had when we did the same thing using method number 1, but method number 1 was a lot shorter. So again, if you have a bunch of different factors, especially linear factors, then I would suggest using this method number 1. But we still have to evaluate this integral. We found that a is equal to negative 1 over 18. Okay, so looking back at a, that becomes a negative 1 over 18. And if you think about this logically, let's look at this integral now. So if we think about this logically, we can pull out that a as negative 1 over 18, the integral of 1 over x dx. And b was a negative 5 over 54. So we can minus 5 over 54, times the integral of, so remember b was over x plus 6, 1 over x plus 6 dx. And then our c value was a positive 4 over 27, times the integral of c was over x minus 3. So 1 over x minus 3 dx. And these are all just equal to natural logs, right? This would be equal to negative 1 over 18, natural log of absolute value of x, minus 5 over 54, natural log absolute value of x plus 6, plus 4 over 27, natural log, absolute value of x minus 3, plus our constant c. Now, if you feel like playing around with this and you want to try to make it into one natural log, because you could, that's fine, but that's just a waste of your time. The point of this is to be able to break down the integrand into smaller pieces that we can integrate. So let's look at another example, and in this case we're going to have repeated linear factors. So when you have repeated linear factors, you have to be really careful on how you break it up. Notice that if you had an x minus r and another x minus r, you wouldn't just list x minus r, x minus r. You would do one once and then twice, and so on. So let's go ahead and factor the denominator in this integral. It's going to be x squared times x plus 1. So when you think about this x squared, this is x times x plus 1. So we actually have factor x. They're the same. Okay, so we have repeated linear factors. And then we have the third x plus 1. So when we break this up, x minus 5 over x squared times x plus 1, it's going to be a over x for the first time you see x, plus b over x squared because we have a second x, plus c over x plus 1. Okay, and the reason why we have to do that is, think about this. If I was to combine all these fractions here, I need the denominator to be x squared times x plus 1. If you left off the square and you just did x plus x, then you wouldn't get back to that same denominator. Now I'm going to use method 1 because I'm lazy. But first I want to clear the fractions. This becomes x minus 5 is equal to a x plus 1 plus b times x plus 1 plus cx squared. So notice that if x is equal to 0, then I have negative 5 is equal to, and the a and the c terms will be gone. If x is 0, I have b right away. B is equal to negative 5. So a good choice for x would be a negative 1, because if I choose x to be negative 1, I have a negative 6 is equal to, and now the first two terms are gone, and I just have cx squared. If x is negative 1, then it's just 1 times c, or c is equal to negative 6. Okay, so I can't choose any other values of x that will get rid of the a and the c and leave me with just b to solve for. So I'm just going to randomly pick some value for x. I'm going to choose x is equal to 1 because that's a small value. And if I plug in 1 for x, negative 5 for b, and negative 6 for c, then I can solve for a. That would give me negative 4 is equal to 2a minus 10 minus 6, I believe. And then solving, we get 6 is equal to a. I'm not going to do method 2. You're free to use method 2. I'm just going to go ahead now and solve this integral. So my integral is going to be equal to, a is positive 6, so I'm going to bring out the 6. It's going to be 1 over x dx. b is negative 5 times the integral of 1 over x squared dx. c is negative 6 times the integral of 1 over x plus 1 dx. Now the first one is natural log of the absolute value of x. This will be 6 times natural log absolute value of x minus 5 times, but this is actually x to the negative 2. So we have to add 1 to the exponent and then divide by a negative 1. It turns into 5 over x minus 6 times the natural log of x plus 1 plus our constant c. And we are done. If you want to practice with using the method 2, that's fine, but I'm not going to. So we've been looking at linear factors, which are real simple, but things can get complicated. Notice that if I were to factor my denominator, I have a common x. I end up with x squared plus 4. That's a quadratic factor, and I can't factor that further because it's a plus, not a minus. When we break up our integrand, the linear factor of x is going to be some a that we need to solve for. Okay? And a is a constant. And the reason why it's just a constant is because the numerator has to be of a smaller degree than the denominator, because that's how our original rational expression was. But now notice that my quadratic factor is an x squared plus 4. So it's possible that the numerator can have an x in it. It just has to be of lower degree than the denominator. So I'm going to have to solve for some bx plus c. Okay? Notice that if I were to combine those two fractions, I end up with the denominator I started with. I'm going to have a problem with this. If I use method 1, it'll probably take me just as long to use method 1 as it will to use method 2. And that's because, and you'll see this after I get rid of the fractions and multiply by the LCD, a is going to be multiplied by x squared plus 4. And I have no x value that will make that 0. And then bx plus c times x. So I could choose x is equal to 0 using method 1. And if x is equal to 0, many things go away and I just have, 0. If x is equal to 0, oops, look what I did. When I got rid of the fraction, I wrote the wrong thing on the left-hand side. This should just be x plus 1. I apologize. So if x is equal to 0, I have 1 is equal to 4a. And I get that a is equal to 1/4, which is fine. But I can't get rid of b or c at this point. So I could just start choosing some small x values. I don't want to choose anything large. Say x is equal to 1. If x is equal to 1, this will be 2 is equal to, now I already know that a is 1/4, so if x is 1, this becomes 5/4 plus b plus c. And then minusing the 5/4 from both sides, I'm going to have 3/4 is equal to b plus c. Okay, but I still have b and c. I haven't solved for it yet. So let me pick another small x value. I could do 2 or maybe -1 might be nice. If x is equal to -1, this becomes 0 is equal to 5/4 plus b minus c after I distribute that -1. Or in other words, -5/4 is equal to b minus c. So at least we now have two equations with two variables. And notice if I just add these together the way they're written, the c is going to go away because I have a plus c minus c. So when I add these two equations together, I'll have 3/4 equal to b plus c. -5/4 is equal to b minus c. The c's will go away. And I'll have -1/2 is equal to 2b. b is equal to -1/4. Now that I have b, I can go ahead and substitute that in to either one of these equations. It really doesn't matter which one I substitute it into. But once I do, I'll get that c is equal to 1. So let's go back to our original expression when we broke it up. We found that a is equal to 1/4, b is equal to -1/4, and c is equal to 1. Okay? So this is how our integral is going to break up. This one is not so nice. So our integral, which started out as x plus 1 over x times x squared plus 4 dx, is going to be equal to 1/4 the integral of 1 over x, that's nice, dx. Okay. plus, you know what, I'm going to leave it the way it is and not factor anything out. I want to look at it for a little bit. Negative 1/4 x plus 1. I cannot write to save my life today. Over x squared plus 4. Did you see what I did up here? I wrote equal instead of plus. And then I have to go ahead and evaluate those two integrals. Well, the first one is not a problem because that's just natural log. The second one, that's a problem. We could pull the 1/4 out. Okay, so first let's look at this first integral, because that's just going to be 1/4 natural log absolute value of x. If I do factor out the 1/4 from the numerator, this is the integral of x minus 4 over x squared plus 4 dx. I don't know how to evaluate that. So I'm going to go ahead and try to split it up again. Notice that this is the integral of x over x squared plus 4 dx minus 4 integral of 1 over x squared plus 4. So this is one possibility, breaking it up in this fashion. Now in this first integral, I think I can just do a u substitution. Maybe I could let u equal x squared plus 4. So du over 2 will end up being x dx. And you see this piece here can be replaced by du. I pull out the 1/2, okay, which will give me the integral, okay, 1/2 on the outside, 1 over u du, which is 1/2 natural log absolute value of u, but u was x squared plus 4. Okay. Now remember, all of this is still with this negative 1/4 in front of it. And in fact, I have a 1/4 natural log absolute value of x still in front of all of this. Okay. Now the next one is x squared plus 4 with a constant on the, or 4 on the outside. That's tangent inverse. So this piece is going to be minus 4 tangent inverse of x over 2 times 1/2. All right, let's put all of this together. This is equal to 1/4 natural log absolute value of x minus, okay, so remember this is all times negative 1/4. So that's going to be minus 1/8 natural log of the absolute value of x squared plus 4. It's going to be a plus 1/2 tangent inverse of x over 2 plus our constant c. Okay, so let's look at another example. What if you have repeated quadratic factors? Well, if you have repeated quadratic factors, Then this is going to be a lot longer than I want it to, but we got to do it. Okay, our denominator is already factored. I have x squared plus 1 to the second power, so I've got 2 of these, right? This is 2 over x squared plus 1, x squared plus 1. So our linear factor x will be a over x, plus our first quadratic factor is going to be a bx plus c over x squared plus 1, plus now we have our second quadratic factor x squared plus 1, so we need that square there, and I'm going to call this dx plus e. Clearing the fractions, we have 2, and I'm going to need space here, is equal to a times x squared plus 1 quantity squared plus parentheses bx plus c times x squared plus 1 plus dx plus e in parentheses times x. In this case, I think I'm going to jump right into method 2. Ooh, that was shaky. And combine like terms. This is a x to the 4th plus 2x squared plus 1. X to the 4th plus 2x squared plus 1. Oh, maybe I shouldn't have done it this way. Oh well, I'm committed to doing it. I think I'm going to leave the bx plus c, and I'm going to distribute this x to get x to the 3rd plus x. Well, at least this is easy, dx squared plus ex. Ax to the 4th plus 2ax squared plus a plus bx to the 4th plus bx squared plus cx cubed plus cx. Is that right? x4 x squared cubed. Yes, that's right. Plus dx squared plus ex. All right, let's combine all our like terms. The highest exponent I have is an x to the 4th. I have a plus b, and I think that's all I have. So a plus b times x to the 4th. And then x to the 3rd is just the cx to the 3rd, I believe, plus cx to the 3rd. Now our x squared is a 2a plus b plus d. So 2a plus b plus d times x squared. X's would be plus c plus e times x, and then my constant is just a. Wow, this is going to be crazy. So let's see what happens though. Notice that on the left hand side I just have 2. I don't have any x to the 4th or x to the 3rd or x squared or x. So those are all just 0, which means that a plus b is equal to 0. Okay, that's for this first one here because I don't have any x to the 4th. Ah, but that's nice because I know that c is equal to 0, so at least we have c. And then 2a plus b plus d is equal to 0 because there's no x squared on the left. And then c plus e is also equal to 0. And a is equal to 2. So right away we have our C and we have our A. So notice in C plus E equal to 0, well, if C is 0, E has to be 0 as well. So once we got rid of all those parentheses, I guess it's not that bad. And now in this first equation, A plus B is equal to 0. I know that A is equal to 2, and B has to be negative 2. So the last thing we need is our D. We have A, B, C, and E. So plugging in all the values into 2A plus B plus D is equal to 0. I'm going to get D is equal to negative 2. Wow, that's going to be fun to break up. Okay, let's go ahead and evaluate our integral. This integral is equal to A is 2, so it's going to be the integral of 2 times 1 over x dx. And B is negative 2, C is 0. Okay. So I'm going to write this out first because I'm not sure what it's going to look like. So negative 2x over x squared plus 1 dx plus the integral of d is negative 2 but e is 0. So this is also a negative 2x in the numerator over x plus 1 quantity squared dx. And it looks like I could bring out those negative 2's. Maybe I can do some u substitutions. Yeah, I think u substitution will be fine. This is equal to 2 times the natural log of the absolute value of x minus 2 times the integral of x over x squared plus 1 dx minus 2 times the integral of x over x squared plus 1 squared dx. And in both of these, I'm going to let I'm going to let u equal x squared plus 1, which gives me du is equal to 2x dx, or du over 2 is equal to x dx. And that will be the same for the last integral if we let, and I'm going to use u, it's a separate integral, it doesn't matter, u be x squared plus 1, and we have du over 2 is equal to x dx. And our integral would be negative 2 times, bring out the 1/2, integral of, this is my du, so it's going to be 1 over u du minus 2 times, bring out the 1/2, integral of 1 over u squared du. So I can cancel these 2's and just have the minus in the front. I'm going to have minus natural log absolute value of u, and u is x squared plus 1, so negative natural log absolute value of x squared plus 1. The 2's will cancel in the second integral. That's going to be minus, so remember this is u to the negative 2, which would turn into negative 1 over u. So this will turn into a plus 1 over u, and that'll turn into 1 over u was x squared plus 1, plus our constant c. Okay, let me bring down this 2 times the natural log absolute value of x. Now again, if you want to try to combine these natural logs, you can, but it's really not necessary. The goal here is to just be able to break. Let's look at this last example. Well, something you should notice right away is this is actually not a rational function because of the e to the x. So I'm going to go ahead and do a substitution and see if I can get it to look like a rational function. The way it's written, I don't know how to integrate this. So I'm going to let u equal the whole denominator 1 plus e to the x. So my du is e to the x dx. Or in other words, du over e to the x is dx. The integral now becomes 1 over u times du over e to the x. But I can't integrate that because I have both the variable u and the variable x. So let's go back up to our u substitution. If u is equal to 1 plus e to the x, then u minus 1 is equal to e to the x. And now I can substitute for e to the x u minus 1. And we have the integral of 1 over u times u minus 1 du. And that's nicely factored. I can go ahead and use my partial fraction. The integrand, 1 over u times u minus 1. Those are linear factors, so I'll have a over u plus b over u minus 1. Clearing the fraction, we have 1 is equal to a times u minus 1 plus b times u. And I think I'm going to use method 1. If u is equal to 1, then b is 1. If u is equal to 0, then a is negative 1. Well, that wasn't bad at all. And my integral is going to be a negative 1 for a, so negative integral of 1 over u du plus b is 1, so 1 over u minus 1 du. And we have negative natural log of u. However, we have to plug back in 1 plus e to the x. Right? So this is going to equal negative natural log of the absolute value of u, but u was 1 plus e to the x. Plus the natural log of absolute value of u minus 1, but u was 1 plus e to the x minus 1. And that's actually really nice because the 1's cancel and you have natural log of e to the x. Well, natural log of e to the x is just x. So this whole piece here is just x. I'm going to bring that out in front because I don't like the negative in the front. And write x minus the natural log of absolute value of 1 plus e to the x plus c. So sometimes you do have to do preliminary steps, but it's fine. Something I did want to point out, although we don't have an example, is here's my caution. If you look at something like the integral of x cubed over x squared plus 1 dx, and we're actually not going to solve this. Notice that the numerator has a larger degree than the denominator, so we can't break that up. Okay? What you first have to do is long division. You have to take the numerator and you have to divide it by the x squared plus 1. Okay. And I'm going to just put some placeholders in here. So this would be a nice review of long division of polynomials. Okay. So I'm going to multiply the x squared plus 1 by x to get x cubed plus, that's a 0 plus x. Okay. And when we subtract, the x's are gone, but remember we're minusing, right? It's x cubed minus. And we have 0x squared minus x plus 0. Well, I'm done, right? Because this is gone. This is nothing. I just have a negative x. What that means is this integral is equal to the quotient is x plus the remainder over the divisor. So it's going to be x plus the remainder over the divisor. And then you would have to break it up after that. We're not going to actually solve this, but I wanted you to see what you would need to do. If the degree on the top is more than the degree on the bottom, you would have to do the long division and then evaluate. So that's it for this section.